You're floating in the void of space, surrounded by infinite darkness, when suddenly a warning light blinks red. Oxygen levels are dropping, temperatures spike. Somewhere, a tiny piece of debris no larger than a grain of sand is hurtling toward you at 17,000 miles per hour. This isn't science fiction. It's the reality astronauts face every time they leave Earth's atmosphere. And it's just one of the countless hidden dangers lurking in the cosmos, silent threats that could turn a routine mission into a nightmare in seconds. Space might look peaceful from down here, a glittering sea of stars and distant planets, but don't let its beauty fool you. Beyond Earth's protective embrace lies a realm of extreme cold, deadly radiation, and forces so powerful they can tear spacecraft apart without warning. Think of it like a cosmic minefield. One wrong move, one overlooked detail, and everything falls apart. And here's the scary part. Many of these dangers aren't just risks for astronauts. They could impact future missions, satellite networks, even plans for colonizing other worlds. That's why today we're pulling back the curtain on space's best-kept secrets, the 25 hidden hazards you've probably never heard of. From solar storms that can disable entire power grids to the bizarre ways microgravity warps the human body, this isn't just a list of scary scenarios. It's a survival guide for anyone curious about what really happens when we venture beyond our blue planet. So strap in, because by the time we're done, you'll never look at the night sky the same way again. The first hidden danger is invisible, silent, and relentless cosmic radiation. Unlike Earth, where our atmosphere and magnetic field shield us, space bombards everything with high-energy particles from supernova, black holes, and even our own sun. These aren't just harmless specks of energy. They're subatomic bullets tearing through spacecraft walls, electronics, and human cells. Every astronaut on the International Space Station receives radiation doses 10 times higher than what we experience on Earth, like getting a full-body CT scan every 5 days. But the real nightmare, future missions to Mars. Without Earth's protection, a round trip could expose crews to radiation levels equal to smoking a pack of cigarettes daily for 30 years, dramatically increasing cancer risks. And it's not just about long-term health. Cosmic rays can cause space brain, a phenomenon where high-energy particles scramble neurons, leading to memory lapses and slower reaction times. Imagine piloting a spacecraft halfway to Mars when suddenly your decision-making slows to a crawl. Even spacecraft aren't safe. These particles can fry circuits, corrupt data, and trigger false alarms, like in 2003 when a solar storm forced astronauts on the ISS to take shelter in a more shielded module as radiation levels spiked. The worst part, we can't fully stop it. Current shielding merely slows particles down, turning them into secondary radiation that's sometimes deadlier than the original. Scientists are racing to find solutions from magnetic force fields to medications that repair DNA damage, but for now, cosmic radiation remains one of the most insidious threats in space. And it's only the beginning of our list. Imagine waking up one day and realizing your legs can barely support your own weight. Your muscles feel like jelly, your bones ache, and you haven't even been sick. That's the reality astronauts face after just a few months in space, all thanks to microgravity's silent sabotage. Without Earth's gravity pulling them down, human bodies start wasting away at an alarming rate. Muscles weaken, bones become brittle, and even the heart, a muscle we rarely think about, starts to shrink from lack of effort. NASA studies show astronauts lose between 1% and 2% of bone density every single month. That's like aging decades in just 1 year. The toll doesn't stop there. Without resistance, muscles atrophy so severely that some astronauts can't stand upright when they return to Earth. After 6 months in space, even seasoned crew members have needed wheelchairs upon landing, their bodies no longer remembering how to fight gravity. Scott Kelly, who spent nearly a year aboard the International Space Station, described feeling like a newborn giraffe, his legs wobbly, his balance completely thrown off. And it's not just strength that's affected. The spine stretches in microgravity, making astronauts temporarily taller by up to 3 inches, only for painful compression to snap everything back into place upon re-entry. To combat this, space agencies have developed some ingenious solutions. The Advanced Resistive Exercise Device, or RED, mimics weightlifting in zero gravity, using vacuum cylinders to create resistance. Astronauts spend over 2 hours a day strapped into this machine just to slow the damage. There are also specialized treadmills with harnesses to simulate walking under load, and vibrating plates that trick bones into thinking they're under stress. But even with these measures, recovery back on Earth can take months, sometimes years. And here's the frightening part: future deep space missions could make it worse. On Mars, with just 1/3 of Earth's gravity, would colonists slowly wither away despite their best efforts? Scientists still don't have all the answers, but one thing's clear: microgravity doesn't just challenge technology. It rewrites what it means to be human, and this threat isn't just for astronauts. As space tourism grows, everyday people could face these risks too, returning from a once-in-a-lifetime trip only to struggle with their own bodies. So while floating effortlessly might look like fun, the truth is far darker. Every second in space is a battle against biology itself, and this is just danger number 2. The sun isn't just a life-giving ball of light. It's also a silent assassin, capable of unleashing explosions so powerful they could vaporize entire civilizations. Solar flares, sudden bursts of radiation, and their more destructive cousins, coronal mass ejections or CMES, are among space's deadliest unscripted threats. These aren't gentle waves of energy, they're tsunamis of superheated plasma, hurling billions of tons of charged particles at speeds topping 1 million miles per hour. And if one hits at the wrong moment, the consequences are unthinkable. Take August 1972, right between the Apollo 16 and 17 missions. A solar storm erupted with such force that astronauts on the moon would have received a lethal dose of radiation enough to kill within hours. Had the timing shifted by just months, we might have witnessed history's first space tragedy. But the danger isn't just about radiation. When a CME slams into Earth's magnetic field, it doesn't just create pretty auroras. It induces massive electrical currents in anything conductive: power grids, satellites, even spacecraft wiring. In 1989, a solar storm knocked out Quebec's entire power grid in under 90 seconds, leaving millions in the dark. But in space, the stakes are even higher. Electronics fry, navigation systems fail, communication goes dead. A single powerful CME could strand astronauts without guidance, cripple life support, or turn a Mars-bound ship into a floating coffin. The International Space Station has shielded safe zones, but deep space crews wouldn't have that luxury. And here's the terrifying twist: we're still learning how to predict these eruptions. The sun gives barely any warning, sometimes just minutes before unleashing catastrophe. NASA's Solar Dynamics Observatory watches the sun like a hawk, but even with cutting-edge tech, a direct hit from a monster storm could set space exploration back decades. Scientists call it the solar kill shot, a rare but plausible event where a CME so powerful wipes out satellites, disrupts global communications, and fries unprotected electronics worldwide. Future missions plan to use water-lined walls or even artificial magnetic fields as shields. But for now, every astronaut venturing beyond low Earth orbit rolls the dice with the sun's temper. And with solar activity ramping up toward its 11-year peak, the next big storm might be closer than we think. Floating above our planet right now isn't just the International Space Station or sleek new satellites, it's a swirling graveyard of human-made wreckage. Space debris, the silent shrapnel of our cosmic ambitions, turns Earth's orbit into a shooting gallery where even a fleck of paint becomes a deadly projectile. At 17,500 miles per hour, the speed of low Earth orbit, a screwdriver can hit with the force of a hand grenade. And it's not just about isolated collisions. This is a problem that multiplies itself in a nightmare scenario scientists call the Kessler Syndrome. Picture this: one satellite explodes, scattering thousands of fragments. Each piece smashes into another object, creating more debris, which then collides with something else, a chain reaction that could eventually encircle the planet in an impassable shell of shrapnel. We've already seen close calls. In 2021, the International Space Station had to fire its thrusters to dodge a chunk of a defunct Russian satellite, a piece no bigger than a suitcase that could have punched straight through its hull. And that wasn't an isolated incident. The ISS regularly adjusts its orbit to avoid debris, sometimes with less than 24 hours warning. Worse yet, we're adding fuel to the fire. Anti-satellite missile tests like Russia's in 2021 create clouds of debris that linger for decades. China's test in 2007 alone spawned over 3,000 trackable fragments, some still zipping around at bullet speeds. Even peaceful missions contribute. Every discarded rocket stage, every loose bolt, every flake of peeling insulation becomes a hazard, the scariest part. There's no easy fix. Lasers to vaporize debris, nets to capture it. These are still experimental. For now, the only solution is tracking and dodging, a cosmic game of chicken played with objects moving 10 times faster than a rifle bullet. And as private companies launch mega constellations of thousands of satellites, the risk grows exponentially. One wrong collision could trigger the Kessler Syndrome, cutting off access to space for generations. So next time you gaze up at the stars, remember what looks like empty space is actually a minefield, one we built ourselves. And unless we clean it up, the final frontier might just become a deadly dead end. The vast emptiness of space isn't just a physical void, it's a psychological abyss. Imagine being trapped inside a cramped metal canister, millions of miles from home, with nothing but blackness stretching endlessly outside your window. Earth is just a pale blue dot, smaller than your fingernail, and every message from loved ones takes 20 minutes to reach you, if they even get through at all. This is the crushing reality of psychological isolation in space, a hidden danger that doesn't just wear down the body but shatters the mind. Astronauts call it the overview effect, that profound shift in perspective when seeing Earth from orbit, a transcendent moment of awe that quickly curdles into existential dread for some. Floating above the world, cut off from every sound, smell, and sensation of home, the human brain starts playing tricks. Sleep becomes fractured, time distorts. Hallucinations creep in, shadows moving where none exist, phantom whispers in the silence, and that's on relatively short missions near Earth. Push farther out toward Mars or beyond, and the isolation becomes unbearable. NASA knows this threat is real. That's why they've turned to one of Earth's most desolate places, Antarctica, as a testing ground. Winter over crews at research stations like McMurdo endure months of total darkness, sub-zero temperatures, and zero escape, mimicking the isolation of deep space. Studies reveal alarming patterns: depression, memory loss, even episodes of psychosis. Some crew members stop speaking entirely, retreating into private worlds. Others develop irrational fixations. One researcher spent weeks convinced a colleague had stolen his socks, obsessing over the crime until it erupted into violence. Then there's the haunting case of astronaut Lisa Nowak. In 2007, this decorated NASA veteran snapped after returning from space, driving non-stop across states in diapers to confront a romantic rival. Her breakdown shocked the world, but insiders knew space changes you. The sheer loneliness, the unrelenting pressure, the knowledge that rescue is impossible if something goes wrong. It rewires the brain, and that's with a full Earth still visible outside the window. On a Mars mission where Earth shrinks to a mere star among millions, the isolation would be incomprehensible. No real-time chats, no emergency returns, just you, your crew, and an ocean of nothingness for years on end. To prepare, space agencies experiment with sensory deprivation tanks, virtual reality, windows showing forests and beaches, even AI companions programmed to mimic human banter. But can pixels and algorithms truly replace the warmth of another soul? Perhaps the most chilling proof of isolation's power lies in an unintended experiment from the early space age. In the 1960s, Soviet scientists placed volunteers in mock spacecraft for months, testing mental resilience. One subject, hidden from history, reportedly lasted only 3 weeks before clawing at the walls, screaming to be released. His final journal entry read, "The silence is eating me alive. As we push farther into the cosmos, this danger won't be solved by better engines or thicker hulls." The real frontier isn't out there, it's inside the human mind. And unlike radiation or debris, there's no shield against the slow unraveling of solitude. Space doesn't just threaten you with radiation or debris, it can kill you in an instant with nothing but empty air, or rather, the lack of it. Vacuum exposure is perhaps the most visceral danger of all, a horror stripped straight from science fiction, except it's horrifically real. The human body, evolved over millions of years for Earth's gentle embrace, has no defenses against the void. One moment, you're safe inside your spacecraft. The next, a tiny crack or a suit failure turns your body into a battleground of physics gone wrong. History gave us a chilling preview of this nightmare during the Voskhod 2 mission in 1965. Soviet cosmonaut Alexei Leonov became the first human to step into open space and almost the first to die there. Just 12 minutes into his spacewalk, his suit ballooned from internal pressure, stiffening so much he couldn't bend his fingers to operate his safety tether. As he struggled, his body temperature spiked, his visor fogged with sweat, and his limbs turned leaden. By the time he forced himself back into the airlock, decompressing in stages to avoid the bends, he was moments from heatstroke and exhaustion. A single design flaw nearly turned a triumph into tragedy. But what if the suit had failed completely? The human body in a vacuum is a grotesque science experiment. Without pressure, saliva boils off your tongue at body temperature. Your eyes might rupture as fluids vaporize. Lungs collapse within seconds, not from suffocation, but from the violent expansion of trapped gases like a balloon popping inward. Your skin swells but miraculously holds, though capillaries burst beneath the surface, painting you in invisible bruises. Consciousness lasts only 10 to 15 seconds, not from lack of oxygen, but because your blood itself fizzes like soda, nitrogen bubbles forming in your veins. NASA-owned tests in vacuum chambers reveal even darker details. In 1966, a technician in a spacesuit test suffered rapid decompression when his hose detached. He passed out in 12 seconds but survived. His last memory was the saliva boiling off his tongue. Animals exposed in early experiments swelled to twice their size, their last moments a silent scream as organs ruptured. It's a fate worse than drowning, worse than fire, because the vacuum doesn't just kill you. It unravels you molecule by molecule. Modern spacesuits are engineered to prevent this nightmare with redundant pressure layers and emergency oxygen. But accidents still lurk: a micrometeoroid puncture, a torn glove during a repair. Even the International Space Station has had close calls. In 2013, astronauts discovered a helmet filling with water during a spacewalk, a malfunction that could have drowned them in their own suits. The terror of vacuum isn't just its lethality, it's the silence. No dramatic explosion, no roaring wind, just the silent, indifferent void claiming another victim. And as we push farther into space with lunar bases and Mars missions on the horizon, this danger won't shrink, it multiplies, because in the end, space isn't hostile. It's simply waiting for us to make one mistake. Moon dust smells like spent gunpowder, a bizarre detail the Apollo astronauts never expected. When Buzz Aldrin first lifted his visor inside the lunar module after walking on the surface, the acrid scent hit him instantly. Neil Armstrong described it as wet ashes in a fireplace, while others compared it to burnt charcoal. But this wasn't just an odd sensory quirk. That dust, finer than powdered sugar and sharper than crushed glass, clung to everything: their suits, their tools, even their eyelashes. And it nearly ruined their mission before they could leave the moon. Turns out, lunar regolith isn't like Earth's dirt. Without wind or water to soften its edges over millennia, each particle remains a jagged, microscopic blade, shaped by eons of meteorite impacts fracturing the surface. Under a microscope, it looks like a collection of shattered shards, some so small they bypass the lungs' natural defenses and embed deep in tissue. The Apollo crews quickly learned the hard way. Inhaling even trace amounts triggered violent sneezing fits, watery eyes, and scratchy throats. Harrison Schmitt of Apollo 17 woke from his moonwalk with full-blown lunar hay fever, his sinuses inflamed for days, and that was after minimal exposure. The real nightmare: future settlements. Picture a lunar base where dust gets tracked inside with every entry, accumulating on surfaces, clogging air filters, grinding away at machinery like cosmic sandpaper. Unlike Earth, there's no rain to wash it away, no atmosphere to oxidize and blunt its edges, just endless abrasive powder waiting to shred lungs, jam door seals, and short-circuit electronics. Apollo's lunar module computers overheated because dust coated their radiators. Spacesuit joints stiffened as particles wedged between moving parts. Even the fine layers clinging to camera lenses nearly blinded mission control to humanity's first steps. And here's what keeps scientists up at night. Prolonged exposure might be deadlier than we thought. Recent lab tests show lunar dust can destroy lung and brain cells at the molecular level, triggering inflammation similar to asbestos. One study exposed human lung tissue to simulated regolith within 24 hours. Over 90% of the cells died. Another found it generates free radicals when mixed with bodily fluids, essentially corroding tissue from the inside. NASA now classifies it as a toxic substance, but on the moon, there's no OSHA to enforce safety protocols. So how do we solve a problem that's literally everywhere? Current ideas range from electrostatic brushes to repel charged particles to liquid coatings that encapsulate dust before it spreads. Some propose entire airlocks with dust showers using magnetic fields or compressed gas. But until we crack this, every moonwalk, every habitat, every bootprint risks bringing in a silent saboteur, one that could turn humanity's grandest off-world ambitions into a slow, suffocating struggle. Because in space, even the ground beneath your feet is out to get you. One moment your spacesuit is baking like an oven, the next it's flash-frozen solid. These aren't just ordinary temperature changes. In space, thermal swings hit harder than anywhere on Earth, creating conditions so extreme they can warp metal and crack diamond. Take the International Space Station. On the sunlit side, surfaces roast at 250 degrees Fahrenheit, hot enough to fry eggs instantly, but swing into shadow, and that same metal plummets to negative 250, colder than Antarctica's deepest winter. And that's just low Earth orbit. Venture farther, and the numbers become surreal. Mercury, the planet closest to the Sun, endures the most violent temperature roller coaster in the solar system. Daylight there soars to 800 degrees, hot enough to melt lead. Yet when night falls, the surface nosedives to negative 290, colder than liquid nitrogen. That's a 1,090-degree swing, enough to turn steel as brittle as glass. How does anything survive? NASA, a messenger probe which orbited Mercury from 2011 to 2015, had to be a masterpiece of thermal engineering. Its sunshield, a ceramic-coated umbrella the size of a ping-pong table, reflected 95% of solar radiation. Meanwhile, the instruments behind it, huddled under layers of insulation thinner than a napkin, kept alive by a delicate dance of heat pipes and radiators. One miscalculation and the spacecraft would have either cooked or shattered. But the real nightmare isn't just the heat or cold, it's the transition. Thermal shock can destroy materials in ways that steady temperatures don't. Imagine pouring boiling water into an ice-cold glass. Now picture that happening to a satellite's solar panels every 90 minutes as it orbits Earth. Each pass from sunlight to shadow makes metals expand and contract like an accordion, stressing joints and wiring until they fatigue. The Hubble Space Telescope's solar arrays suffered this exact torment, warping so severely during temperature swings that engineers had to design replacements mid-mission. And then there's the Moon. Apollo astronauts quickly learned that lunar dust wasn't their only foe. Their suits, designed to handle space's vacuum, nearly failed under thermal stress. Sun-facing patches of white fabric hit 250 degrees, while shadowed sections plunged to negative 280. The gloves were especially treacherous. Gripping a sunlit tool could burn their fingers, while touching equipment in shadow risked instant frostbite. Some reported their boots growing painfully hot on the surface, only to freeze solid when lifted slightly into shade. Modern spacecraft use ingenious tricks to cope. Heat pipes filled with ammonia shuttle warmth from hot zones to cold ones. Multi-layered insulation blankets, some thinner than a credit card, reflect radiation while trapping air pockets for stability. The James Webb Space Telescope even deployed a 5-layered sunshield the size of a tennis court, creating a temperature difference of 600 degrees between its blazing front and icy back. But for all our ingenuity, nature always finds flaws. In 2010, the Solar Dynamics Observatory caught a solar panel cable warping violently during an orbital sunrise, nearly snapping. Satellites in geostationary orbit often suffer noonday demons, brief moments when sunlight reflects off Earth just right, superheating one side while the other remains in deep freeze. Even spacecraft materials themselves can turn traitor. Aluminum, beloved for its lightness, becomes brittle at cryogenic temperatures, while specialized lubricants thicken to sludge in shadow. The terrifying truth: we've barely scratched the surface of extreme thermal environments. Venus lead melting heat, Europa's negative 300-degree ice sheets. The boiling geysers of Enceladus. Each new destination demands entirely new ways to keep machines, and someday humans, from being simultaneously fried and frozen. Because in space, the weather forecast is always the same, deadly no matter where you stand. Time slows down when you leave Earth, not in some poetic sense, but literally. This is Einstein's theory of relativity in action, and it's not just a thought experiment. Every GPS satellite orbiting Earth experiences it firsthand, ticking 38 microseconds faster each year than clocks on the ground. That tiny difference, it's enough to throw off navigation by miles if engineers didn't account for it. But what happens when we push farther into space, where gravity weakens and speeds increase? The numbers get wilder, and so do the consequences for human travelers. Picture identical twins. One stays on Earth, the other embarks on a 10-year mission to Mars. When the astronaut returns, they'll be ever so slightly younger than their sibling by about 23 milliseconds. That doesn't sound like much until you scale it up. A voyage to a star system near light speed could make the traveler return to find everyone they knew long dead while they've barely aged. This is the twin paradox, a real-world quirk of physics that's as mind-bending as it is unsettling. Here's why it happens. Time isn't the constant we think it is. It's elastic, warped by gravity and velocity. The stronger the gravity, like Earth's pull, or the faster you move, the slower time crawls for you relative to someone in a weaker field or at rest. Satellites experience less gravity in orbit, so their clocks run faster. But for astronauts traveling at extreme speeds, time slows down onboard compared to Earth. This isn't science fiction, it's been measured with atomic clocks on airplanes and in space. Now imagine the implications for deep space colonies. Generations born on a high-gravity world or a ship near light speed might age decades slower than their Earth cousins. Communication between planets could become a temporal minefield. Video calls where one side visibly ages faster than the other. Even synchronization between fleets would require constant adjustment. Forget time zones, we'd need relativity calculators just to schedule meetings. The most disturbing part, there's no workaround. This isn't a problem we can engineer our way out of, it's woven into the fabric of the universe. For now, the effects are minuscule for human missions, but as we reach for the stars, time itself becomes another silent adversary, one that doesn't just challenge our technology but reshapes our very understanding of existence. And that's a danger no spacesuit can shield against. The moment Neil Armstrong and Buzz Aldrin splashed down after humanity's first moon landing, they weren't greeted with parades or press conferences. They were sealed inside a mobile quarantine facility like characters in a sci-fi horror movie. NASA wasn't taking chances. What if they'd brought back something alien? That same fear haunts scientists today, not with moon rocks but with Mars. Because lurking beneath the red planet's rusty surface could be microbes unlike anything on Earth, and our rovers might accidentally give them a one-way ticket home. This isn't just paranoid fiction. Planetary protection protocols exist for a reason. Every spacecraft sent to Mars undergoes sterilization so rigorous it would put a hospital to shame. Components are baked at 250 degrees Fahrenheit for days, bathed in radiation, and sealed in clean rooms where technicians resemble hazmat-suited surgeons. The Viking landers of the 1970s were so pristine, their heat shields were sterilized with vaporized hydrogen peroxide, a process normally used to decontaminate biological weapons labs. Even Curiosity, which carries a drill capable of reaching subterranean water, follows contamination rules so strict its operators must prove no Earth bacteria could survive the journey. But here's the terrifying loophole: we can't guarantee perfection. In 2013, researchers discovered a strain of bacteria inside a cleanroom at the European Space Agency, a microbe so resistant to sterilization it thrived on eating metal and radiation. If something like that hitchhiked to Mars, it could skew our search for life or, worse, mutate in ways we can't predict. The reverse is just as chilling. NASA Perseverance rover is collecting samples for eventual return to Earth. What if a dormant Martian organism, frozen for eons in clay or ice, wakes up in a lab? History offers grim precedents. When European explorers brought back plants and animals from the New World, they triggered ecological chaos. Rats decimated crops, smallpox ravaged indigenous populations. Now imagine that scenario with an organism that doesn't share a single evolutionary ancestor with life on Earth. It might not attack humans directly. It could be a silent saboteur, a microbe that corrodes electronics, consumes concrete, or outcompetes Earth bacteria in ways that collapse ecosystems. Science fiction loves this trope. Films like The Andromeda Strain and Life depict alien pathogens melting through containment labs. Reality is more subtle and perhaps scarier. Real planetary protection officers worry about false positives, Earth microbes disguising themselves as Martian life. Or worse, Martian microbes so alien we don't even recognize them as life until it's too late. That's why Mars sample return missions will use multiple layers of fail-safes, sealed containers, robotic transfers in orbit, and biosafety facilities with negative pressure and autoclaves capable of incinerating any escapees. But perfection is a myth. One cracked seal, one software glitch, one scientist underestimating a microbe's ability to cling to a glove. The irony: after spending billions to find life elsewhere, our greatest challenge might be making sure it never comes home. You're hurtling toward the Martian surface at 1,000 miles per hour when the engines sputter. Alarms scream, the landing sequence is failing. You shout commands into the mic, but no one hears you. Not yet, because by the time your panicked voice reaches Earth, 20 long minutes will have passed, and by the time help replies, another 20. In that agonizing 40-minute void, you're utterly alone. This is the nightmare of communication lag, a silent killer lurking in the vast distances between worlds. Consider Apollo 11's descent to the moon. As the lunar module dropped toward the surface, it passed behind the moon's bulk, severing contact with Earth for 13 harrowing minutes. Mission Control could only stare at their consoles, gripping coffee cups gone cold, while Armstrong and Aldrin navigated boulder fields and dwindling fuel with zero guidance. Those minutes felt like eternity, yet that was just a cosmic hiccup compared to Mars. The moon's a quick text message away. Mars is a snail mail letter. Even light, the fastest thing in the universe, takes an average of 12 minutes to cross the gulf, with delays stretching to 22 when the planets are farthest apart. Now picture this playing out during a medical emergency. An astronaut collapses, their suit readings spiking with indicators of a stroke or cardiac event. The crew's medic scrambles for instructions, but the best doctors on Earth are watching events that already happened. Every diagnosis, every treatment step arrives too late. NASA trains astronauts for this grim reality with delayed comms, drills simulations where crews must perform complex procedures, even surgeries, without real-time input. Some scenarios force them to wait deliberately before receiving critical data, conditioning them to act first and hope for confirmation later. The ripple effects go beyond emergencies. Routine operations become fraught with uncertainty. A rover exploring Martian cliffs can't be joysticked in real time. Each movement requires painstaking pre-programming. During the Curiosity landing in 2012, the 7 minutes of terror were actually 14 minutes of helplessness on Earth. The rover had already succeeded or crashed by the time signals reached Mission Control. Future human colonies would face eerie social disconnects, video calls with loved ones reduced to staggered monologues, laughter arriving minutes after the joke, conversations unfolding like disjointed letters from the 19th century. And here's the psychological toll. That delay isn't just technical, it's existential. Every transmission from Mars carries an unspoken reminder of your isolation. Earth isn't just far away, it's trapped in the past. You could be dead already, and home wouldn't know for 20 minutes. Scientists call it the disconnection dissonance, a mental fracture where the brain struggles to reconcile that the vibrant, real-time Earth in your memories is now a delayed broadcast, like watching your own life on tape delay. There's no workaround. No magic tech can make light travel faster. Proposed solutions range from AI co-pilots making split-second decisions to laser relays that at least maximize data speed. But until we bend the laws of physics themselves, every utterance into the void will come with that chilling pause, the silence of the cosmos reminding us just how small we really are. Earth's magnetic field is like an invisible force field wrapping our planet in a protective bubble. Most of us never think about it until we step beyond its reach. This colossal shield deflects charged particles from the sun and deep space, bending them away before they can rip through our DNA. But venture into deep space or land on Mars, and suddenly that protection vanishes, leaving astronauts exposed to a rain of radioactive bullets. The difference is staggering. On Earth, even during a solar storm, our magnetic field funnels most dangerous particles toward the poles, creating dazzling auroras while keeping populated areas safe. But the International Space Station, orbiting just 250 miles up, already sits where the field weakens, receiving radiation levels 10 times higher than the surface. Now imagine Mars. Billions of years ago, the red planet lost its magnetic dynamo, leaving its atmosphere to be stripped away by solar winds. Today, Mars' surface gets bombarded with radiation 50 times more intense than Earth. A single solar flare there could deliver a lethal dose in hours. We've seen glimpses of this danger in action. In 2003, during one of the strongest solar storms ever recorded, astronauts on the ISS had to retreat to the most shielded module, huddling as radiation levels spiked. Meanwhile, down on Earth, most people didn't even notice our magnetic field absorbed the worst of it. But Mars' NASA Curiosity rover measured radiation there for over a decade, revealing that a round-trip mission would expose astronauts to the lifetime radiation limit set by most space agencies. Prolonged stays could mean irreversible cell damage, spiked cancer risks, and even cognitive decline from neuron damage. Scientists have wild ideas for artificial solutions: magnetic umbrellas the size of cities, underground lava tube habitats, even genetically engineering radiation-resistant astronauts. But for now, every mission beyond Earth's magnetic embrace is a gamble. The universe is firing radioactive bullets at us every second. We just never notice because Earth's silent, spinning shield has our back. Until we leave home, then the real danger begins. The year was 1971, and the Soyuz 11 mission was about to make history, until a silent killer stole the lives of 3 cosmonauts in less than a minute. Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev had just spent 23 days in space, a record at the time, and were moments from triumph. Their descent capsule separated smoothly, parachutes deployed, but when recovery teams opened the hatch, they found all 3 men slumped motionless in their seats, faces dotted with dark blue splotches. A tiny valve, no bigger than a coin, had cracked open during re-entry, venting their cabin into the void. The crew suffocated before they could even react. This is the horror of explosive decompression, a danger where the very air keeping astronauts alive turns traitor. The physics behind it is brutally simple, Boyle's law. When pressure drops suddenly, gases trapped in the body expand violently. Imagine your lungs, normally delicate sacs handling gentle breaths, forced to balloon like overfilled balloons as the atmosphere vanishes. At 30,000 feet, you might have 15 seconds before passing out. In space, the vacuum can kill in under 10. Blood boils in your veins, saliva vaporizes on your tongue. Eardrums rupture inward, and unlike slow leaks where alarms might give precious seconds to don oxygen masks, explosive decompression offers no warning. Just a deafening roar of rushing air, then silence. The Soyuz 11 disaster exposed terrifying design flaws. The valve wasn't supposed to open until 2 miles above Earth, but vibrations from separation shook it loose at 100 miles up. The crew had no pressure suits. Early Soyuz missions deemed them unnecessary for re-entry, so when disaster struck, their bodies bore the full brunt. Autopsies revealed hemorrhages in their brains, lungs, and eardrums, the telltale signs of embolism, bubbles forming in bodily fluids as dissolved gases burst free. Modern spacecraft now use multiple redundant seals and rigorous testing to prevent repeats. Spacesuits are mandatory during risky phases, but the threat still lingers. In 1995, a Mir space station crew faced panic when a Progress supply ship collided, puncturing a module. They barely sealed the hatch in time. And in 2018, the ISS detected a tiny drill hole in a Soyuz capsule, later suspected as sabotage. That could have led to a slow, deadly leak. The scariest part: we can engineer against mechanical failures, but human error is unpredictable. A single forgotten tool, a cracked seal overlooked in inspection, or a micrometeoroid strike in just the wrong spot, and history could repeat itself. Because in space, even the air you breathe is a liability waiting to betray you. You'd think space food is just about taste. Freeze-dried ice cream for the novelty, maybe some bland noodles for practicality. But here's the terrifying reality. Radiation isn't just frying astronauts' DNA. It's stealthily robbing their meals of vital nutrients, turning carefully planned diets into empty calories halfway through a mission. Those foil-wrapped meals on the International Space Station, some have been sitting in orbit for over a decade. bombarded by cosmic rays that systematically dismantle vitamins molecule by molecule. NASA studies show certain nutrients degrade by 40% in just 2 years. Imagine subsisting on food that's nutritionally barren by the time you eat it. Take vitamin C, the antioxidant that keeps everything from vision to immune systems functioning. On Earth, oranges lose about 2% of their vitamin C monthly. In space, radiation accelerates the process exponentially. Astronauts on year-long missions could be chewing what looks like a balanced meal, only to receive half the intended nutrition. The consequences aren't just fatigue. Scurvy has reared its head in modern spaceflight, with crew members reporting gum bleeding and joint pain until emergency vitamin supplements arrived on resupply ships. This isn't hypothetical. During the Skylab missions in the 1970s, astronauts discovered their spinach had turned to flavorless mush, its folate and iron obliterated. Today's meals fare slightly better. Thermostabilized pouches and irradiated meats extend shelf life, but at a cost. Thiamine, crucial for nerve function, plummets in irradiated beef. Vitamin K, vital for blood clotting, vanishes from processed vegetables. Even water becomes a concern. When NASA tested 50-year-old water from the Apollo era, they found traces of degraded plastic leaching into it from storage bags. The solution, surprisingly low-tech. The ISS now hosts vegetable growth chambers not just for fresh greens, but for living nutrient factories. Red romaine lettuce grown in microgravity has higher antioxidant levels than Earth counterparts, a desperate hedge against vitamin loss. Future lunar bases might rely on hydroponic towers of spirulina, an algae packing 30 times more beta-carotene than carrots. China's space program has even experimented with growing rice in orbit, seeking staples that replenish rather than deplete. But here's the unspoken fear. What happens when missions stretch beyond resupply range? Mars-bound ships can't receive emergency vitamin drops. One miscalculation in food degradation rates, and colonists could face catastrophic deficiencies mid-journey. Muscles wasting, bones weakening, brains fogged by lack of essential fatty acids. It's a slow-motion time bomb disguised as dinner, and unless we crack the code of self-sustaining space agriculture, humanity's greatest voyages might be sabotaged by something as simple as a rotting tomato. Imagine floating weightless, gazing at Earth through a window only for your stomach to lurch violently as your brain screams that you're tumbling headfirst. This isn't seasickness, it's space adaptation syndrome, and it turns even veteran astronauts into disoriented, green-faced newcomers for days. Roughly 60% of space travelers experience this inner ear rebellion. Their vestibular systems, the delicate balance machinery in our skulls, flooded with conflicting signals. On Earth, gravity tells us which way is down. Fluid in the inner ear's canals shifts with movement, letting us walk without stumbling, but in microgravity, those fluids float aimlessly like unmoored buoys in a storm. The result, your eyes say you're stationary while your inner ear insists you're spinning. The brain's response is brutal, immediate nausea. Footage from early shuttle missions shows seasoned test pilots reduced to clutching vomit bags, their faces clammy. NASA astronaut Jake Gahn's bout was so legendary the agency jokingly coined the Gahn scale to measure sickness severity. Then there's the infamous vomit comet training flights, planes that simulate weightlessness in steep dives, where even veteran spacewalkers have been caught off guard, suddenly heaving mid-float. The irony, some astronauts adapt after a few days, only to suffer re-entry sickness when gravity returns, their Earth-calibrated inner ears now treating solid ground as the anomaly. But the real danger isn't just discomfort. Severe disorientation can derail critical missions. During the STS-41D shuttle launch in 1984, astronaut Mike Mullane recalls fighting dizziness so intense he couldn't read checklists, a terrifying scenario when every second counts. Others report phantom sensations of being upside down even when right side up, leading to dangerous miscalculations. Picture reaching for a control panel only to miss because your brain swapped up and down. Some crew members resort to keeping lights off until adaptation kicks in, avoiding visual cues that worsen the conflict. Scientists are still unraveling why some astronauts adapt faster than others. Balance training, spinning chairs, virtual reality helps somewhat, but there's no magic pill. Future Mars missions could face grueling months of crew members drifting between nausea and vertigo, their productivity crippled by something as primal as inner ear confusion. And here's the kicker: artificial gravity might not fully solve it. Spinning habitats could introduce new dizzying cues, trading one form of disorientation for another. The takeaway: space doesn't just challenge our technology, it hacks our biology at the most fundamental level. Because sometimes the greatest danger isn't radiation or debris. It's your own body betraying you. Cosmic radiation from our sun is dangerous enough, but lurking between the stars is something far worse. Galactic cosmic rays, or GCRS, are the heavyweight champions of space radiation, packing energies so extreme they make solar particles look like BB guns. While solar radiation comes in furious bursts during flares, GCRS are the silent, constant rain of atomic shrapnel from exploded stars and black holes across the galaxy. These aren't just protons and electrons, they're the nuclei of iron, nickel, even uranium atoms stripped of their electrons and accelerated to near light speed. When one slams into a spacecraft hull, it doesn't stop at the surface like solar particles might. It blasts straight through, splintering into a deadly shower of secondary particles as it goes. The difference is like comparing a pebble tossed at your window to a cannonball. Solar radiation might scorch your skin, but GCRS tunnel deep into bone marrow, organs, and worst of all, the brain. A 2013 study at Johns Hopkins exposed mice to simulated GCR doses equivalent to a Mars mission. Within weeks, the mice showed alarming signs of neural degeneration, their brains riddled with damaged neurons and protein clumps eerily similar to Alzheimer's patients. Autopsies revealed inflamed neural pathways and crippled cognitive function. Some mice forgot familiar maze routes they'd mastered before exposure. Translate that to humans, and the implications are chilling. Astronauts could reach Mars only to find their memories fraying, their decision-making slowed, their very personalities eroding under the invisible assault. Shielding against GCRS is a nightmare. Aluminum hulls, useless, the high-energy particles smash into the metal's atoms, creating a cascade of even more dangerous secondary radiation. Water and polyethylene help somewhat, but you'd need walls several feet thick to make a dent, adding impossible weight to spacecraft. NASA proposed magnetic deflectors inspired by Earth's magnetosphere might redirect some particles, but GCRS are so energetic that many would barrel straight through the fields anyway. The Apollo crews got lucky. Their brief trips coincided with a period of unusually low GCR activity, but future Mars colonists won't have that luxury. During solar minimum, when the sun's magnetic field weakens and stops deflecting some GCRS away from the inner solar system, radiation levels can spike by 30%. That's like trading a daily chest X-ray for a full-body CT scan. Even worse, GCR damage is cumulative. There's no healing between exposures, just a slow, irreversible buildup of cellular carnage. So while we fret about solar storms and oxygen leaks, these galactic bullets keep firing relentlessly from the void. They don't announce themselves with flashing lights or blaring alarms. They just pierce through everything: metal, flesh, bone, rewriting the blueprint of life itself, one atomic collision at a time. And unlike other space dangers, this one doesn't just threaten missions. It threatens minds. Astronauts don't just battle radiation and muscle loss, they wage a silent war against exhaustion so severe it can turn routine tasks into life or death gambles. On the International Space Station, crews average just 6 hours of sleep per night, a far cry from the 8.5 hours NASA recommends. The reasons: a relentless barrage of noise ventilation fans humming at 70 decibels, constant equipment beeps, and the disorienting spectacle of 16 sunrises and sunsets every 24 hours. Our bodies evolved for the steady rhythm of Earth's day-night cycle, but in orbit, circadian rhythms crumble like sandcastles against a tide of artificial light and chaos. Enter the sleep pod, a claustrophobic closet barely larger than a coffin, where astronauts strap themselves into sleeping bags velcroed to the walls. Earplugs and eye masks are mandatory, yet many report waking multiple times, their bodies convinced it's midday when the station clocks say it's night. The consequences aren't just groggy mornings. Chronic sleep deprivation impairs judgment as severely as alcohol intoxication, a terrifying prospect when you're maneuvering multi-ton spacecraft or handling toxic fuels. The infamous 1997 Mir collision, where a sleep-deprived crew misjudged a docking test and sent a Progress supply ship plowing into the station's Spectre module, nearly ended in catastrophe. Oxygen hissed into space as the crew scrambled to seal hatches, their reflexes dulled by months of fractured rest. Post-accident analysis revealed crew members had been surviving on 4 to 5 hours of sleep for weeks, their error rates spiking as fatigue rewired their brains. Scientists are fighting back with melatonin experiments, testing whether this natural sleep hormone can override the chaos of space's light-polluted nights. Early results are mixed. Some astronauts report deeper sleep, while others find their dreams invaded by vivid, disorienting hallucinations. The stakes couldn't be higher. Future Mars missions, with their 24.5-hour sols slightly longer than Earth days, could push circadian confusion to new extremes. Imagine trying to sleep while your body insists it's time for lunch, all while knowing a single lapse in attention could doom your crew. And here's the cruel twist: even when astronauts manage to sleep, they wake feeling unrested. Without gravity's gentle pull, bodily fluids pool in the head, creating a constant stuffy sensation akin to a cold. Snoring vanishes in microgravity, but so does the restorative deep sleep our brains crave. Studies show spacefarers spend markedly less time in REM sleep, that critical phase where memories consolidate and emotions process. The result: crews on long missions often report mood swings, irritability, and foggy recall. Like living in a perpetual jet-lagged haze, the solution might lie in technology mimicking Earth's rhythms. The ISS now uses LED lighting that shifts from blue-white daylight to amber sunset cues, while future lunar bases could employ blackout schedules and soundproofed sleep chambers. But until we crack this, every astronaut remains one sleepless night away from a mistake that could echo through history. Because in space, fatigue isn't just discomfort, it's a countdown to disaster. Beneath the swirling ammonia clouds of Jupiter, storms rage with a violence that dwarfs anything Earth could conjure. These aren't just thunderstorms, they're planet-sized tempests where lightning bolts erupt with 1,000,000 times the energy of their terrestrial cousins, each strike powerful enough to vaporize a skyscraper. NASA Juno probe, orbiting the gas giant since 2016, has recorded flashes so intense they'd appear brighter than the sun if seen up close. But what makes these storms truly alien isn't just their scale, it's their eerie soundtrack. Converted from radio emissions, the crackling, space thunder of Jupiter's lightning sounds less like earthly rumbles and more like the pops and hisses of a deranged cosmic radio station. The physics behind these monstrous discharges is both familiar and alien. Like Earth, Jupiter's lightning forms when charged particles collide in turbulent atmospheres, but there the recipe gets twisted. Clouds of ammonia and water churn hundreds of miles deep, while temperatures swing from -200 degrees at the cloud tops to a broiling 3,000 degrees deeper down. This creates a conductive slush where electrons leap between layers, birthing bolts up to 1,000 miles long. Juno's instruments detected one particularly vicious storm near Jupiter's north pole, where flashes occurred 3 times per second, a strobe light of destruction flickering non-stop for months. Surviving this electrical hell requires armor worthy of a science fiction warship. Juno's delicate electronics hide inside a 200-kilogram vault of titanium, a metal chosen for its ability to absorb radiation and dissipate heat. Even then, mission planners had to accept that some systems would slowly cook. Juno's camera, for instance, was designed to fail after just 37 orbits, its lenses eventually fogged by relentless radiation. But without that titanium shield, the probe wouldn't last a single pass. Lightning isn't the only threat. Jupiter's magnetic field accelerates electrons to near light speed, creating a particle storm that bombards everything in its vicinity. The most haunting evidence of these storms isn't visual, it's auditory. When Juno's Waves instrument captured the radio pulses from Jupiter's lightning, scientists converted the signals into sound waves audible to human ears. The result, a chorus of pops and crackles like static from a television left on too long, punctuated by deep, resonant booms that seem to echo across space itself. These aren't true sounds. Space has no air to carry them, but listening to the translated emissions feels like eavesdropping on the planet's raw, untamed fury. Here's what chills scientists. Jupiter's storms might be a preview of what lurks on exoplanets. Gas giants orbiting close to their stars, known as hot Jupiters, could host lightning even more extreme, their searing temperatures and violent winds creating permanent supercell thunderstorms. Juno's data hints that similar phenomena might occur deep within Saturn or Uranus, where exotic forms of lightning could ignite in oceans of metallic hydrogen or supersonic water. For now, Jupiter remains the king of cosmic storms, a reminder that beyond Earth's gentle skies, the universe specializes in extremes we're only beginning to understand. And as Juno's titanium husk continues its dances through this electric gauntlet, each crackle of space thunder it records is a message from a world where the weather doesn't just kill, it annihilates. A speck of space dust no bigger than a grain of sand streaks past Earth at 40,000 miles per hour faster than a bullet. Now imagine something the size of a marble. That's all it took in 2013, when a 6,600-ton asteroid exploded over Chelyabinsk, Russia, with a force of 500 kilotons, 30 times stronger than Hiroshima. The shockwave shattered windows 6 miles away, injuring over 1,500 people. And here's the terrifying part: no one saw it coming. The rock approached from the sun's glare, invisible until it was too late. But space doesn't need boulders to wreak havoc. Even millimeter-sized debris can be catastrophic. In 2020, astronauts on the International Space Station woke to a nightmare, a slow, persistent hiss. A tiny meteoroid, smaller than a fingernail clipping, had punched through the Soyuz capsule docked to the station. The leak drained precious oxygen until crew members scrambled to patch it with epoxy and tape. That minuscule hole could have been deadly if it had struck a few inches to the side, severing critical wiring or piercing a crew member's suit during a spacewalk. The solution: Whipple shielding, a brilliant design that turns spacecraft hulls into cosmic bulletproof vests. Named after astronomer Fred Whipple, this multi-layered armor doesn't try to stop projectiles head-on. Instead, it lets them smash through a thin outer shell, vaporizing on impact, while a spaced inner layer catches the resulting debris cloud. Picture a watermelon wrapped in aluminum foil. When a BB gun hits it, the foil ruptures, but the fruit inside stays intact. The ISS uses over 100 layers of Kevlar and Nextel in its shielding, a quilt of high-tech materials that dissipates energy like a spiderweb absorbing a fly. Simulations reveal the stakes. A grape-sized rock at orbital speeds hits with the kinetic energy of a bowling ball dropped from a skyscraper. Satellite cameras have captured the aftermath: gaping craters in solar panels, shredded insulation blankets, and circuitry fried by plasma generated on impact. In 1993, Europe's Olympus communications satellite was crippled by a micrometeoroid strike during the Perseid meteor shower, losing attitude control and spiraling uselessly until its batteries died. The math is sobering, with over 130 million artificial debris fragments orbiting Earth, plus countless natural meteoroids. Every spacecraft is essentially sailing through a shotgun blast. NASA tracks objects down to 2 inches wide, but anything smaller slips through the net. And at those speeds, even a paint chip can crack a windshield. Future lunar bases might need regolith-covered roofs, while Mars-bound ships could deploy sacrificial bumper modules to absorb hits before they reach crew areas. But the ultimate irony, the very technology shielding us creates more hazards. Every collision spawns new debris, feeding the cascade of fragments that make space deadlier with each passing year. It's a vicious cycle, one where humanity's foothold in the cosmos hinges on outsmarting specks of rock moving faster than rockets themselves. Mark Watney, the fictional astronaut in The Martian, famously grew potatoes in Martian soil to survive, but here's the brutal truth science uncovered after the book was published. That dirt would have poisoned him within weeks. Lurking in Mars' rusty surface is a silent killer called perchlorates, salts so toxic they attack the human body at a molecular level. NASA Phoenix lander first detected these chemicals in 2008, and subsequent rovers confirmed they're everywhere. Up to 1% of Martian topsoil consists of this corrosive substance. Perchlorates aren't your average table salt. Their molecular structure contains chlorine and oxygen atoms arranged in a way that wreaks havoc on biological systems. When ingested or inhaled, they bind to iodine receptors in the thyroid gland, effectively starving it of the element crucial for hormone production. The result? A slow, insidious shutdown of metabolism, leading to weight fluctuations, muscle weakness, and in severe cases, myxedema coma, a life-threatening condition where the body's systems grind to a halt. Chemical diagrams reveal the damage at a cellular level. Thyroid follicles, normally neat little spheres that produce hormones, become swollen and chaotic under perchlorate assault, like deflated balloons tangled together. The danger isn't theoretical. On Earth, perchlorate contamination near rocket test sites has caused measurable health impacts. In Henderson, Nevada, a chemical spill led to perchlorate levels in groundwater reaching 24 parts per billion. Just a fraction of Mars concentration, yet residents showed significant thyroid dysfunction. Now imagine breathing dust with thousands of times that toxicity every day. Future Mars colonists couldn't just brush off their suits after a walk. They'd need full decontamination protocols akin to hazmat teams cleaning up chemical spills. Here's where the Martian got it fatally wrong. Watney's potato farm would have been a death trap. Mars dirt isn't just a little salty, it's laced with enough perchlorates to stunt plant growth and bioaccumulate in crops. Even if the potatoes grew, eating them would deliver concentrated doses straight to his endocrine system. NASA studies on simulated Martian soil show plants absorb these toxins readily, their roots acting like straws sucking up poison. Some microbes can break perchlorates down, but not fast enough to matter for human consumption. Solutions exist, but they are far from simple. Proposed Mars washing techniques involve rinsing soil with bacteria-laden water to metabolize the salts, or electrochemically stripping perchlorates using specialized reactors. Both methods would require hefty equipment no stranded astronaut could improvise. Others suggest gene-editing crops to resist uptake, creating a botanical filter between soil and dinner plate. Until then, every scoop of Martian dirt remains a toxic time bomb, one hidden danger no amount of duct tape and ingenuity can easily fix. Oxygen keeps us alive until it turns traitor. What most don't realize is that the very gas we breathe becomes poison under pressure, a danger NASA learned tragically during the Apollo 1 disaster. The capsule's pure oxygen environment, pressurized to 16 pounds per square inch for launch, turned a minor electrical spark into an inferno that killed astronauts Gus Grissom, Ed White, and Roger Chaffee in seconds. Flames raced along wiring and nylon netting with terrifying speed, fueled by oxygen's relentless chemistry. At high concentrations, this life-giving gas morphs into an accelerant so aggressive it makes even steel burn. Modern spacecraft avoid this nightmare by mimicking Earth's air mix: 21% oxygen, 78% nitrogen, a balance refined over millions of years of evolution. But Apollo's designers opted for 100% oxygen at reduced pressure in flight, a gamble meant to simplify systems. The logic seemed sound: lower pressure reduces fire risk, right? Yet in testing, NASA discovered a horrifying quirk. A glove left in pure oxygen at 5 pounds per square inch could spontaneously combust if crushed, no spark required. The agency's own technicians nicknamed the Apollo cabin a bomb waiting to happen long before the fatal test. The deeper science is even more unsettling. Oxygen toxicity isn't just about fire. Breathe it at elevated pressures, and the gas attacks the nervous system like a neurotoxin. Deep sea divers know this well. Go below 180 feet on regular air, and the risk of underwater seizures spikes. The same danger haunts spacewalks. During the Gemini 9 mission in 1966, astronaut Gene Cernan's suit nearly overheated as he struggled with a stuck visor, his exertion spiking oxygen absorption. Had his rig malfunctioned, flooding his helmet with pure O2, he might have convulsed mid-float, a gruesome fate later simulated in Navy labs where test subjects twitched violently before blacking out. Zero gravity adds another twist to the fire hazard. On Earth, flames taper upward as hot air rises, but aboard the ISS, fires burn in eerie, slow-motion spheres. NASA's flame extinguishment experiment revealed this in haunting footage: blobs of flame curling inward on themselves, lingering far longer than their terrestrial counterparts. Without gravity to pull cooler air downward, oxygen clings to the combustion zone, creating self-sustaining fireballs. A single electrical short could spawn one of these floating death globes, bouncing unpredictably until it finds more fuel. The solution: redundancy and vigilance. The ISS monitors oxygen levels down to the 0.1%, with automatic nitrogen injectors ready to dilute any spike. Spacesuits use lower O2 pressures during risky operations, trading slight breathlessness for safety. Yet the threat never fully vanishes. Every spacecraft, every moon base, every Mars habitation module must walk the razor's edge: enough oxygen to sustain life, but not so much that it turns the air itself into a silent executioner. Because in space, even the act of breathing carries hidden stakes. Remember that stomach-dropping moment in Interstellar when the crew approaches the supermassive black hole Gargantua? The way their ship groans under invisible forces as time itself warps around them, that wasn't just Hollywood drama, it was gravity's ultimate trap in action. These cosmic monstrosities don't just pull, they stretch, twist, and shred anything that ventures too close in a process scientists call spaghettification. And the math behind it is even more terrifying than the movies show. Take Sagittarius A, the black hole at our galaxy's center. Approach within 6 million miles, a stone's throw in cosmic terms, and the tidal forces hit like an atomic scale rack. Your feet closer to the black hole would feel gravity exponentially stronger than your head. That difference isn't just uncomfortable, it's catastrophic. For an average human, the stretching force would surpass 20,000 newtons per kilogram. To put that in perspective, Earth's gravity pulls at just under 10 newtons per kilogram. Within seconds, your body would elongate like taffy, bones snapping apart molecule by molecule as you're stretched into a stream of atoms swirling toward oblivion. But black holes aren't the only gravity wells with this power. Neutron stars' corpses of exploded suns so dense a sugar cube-sized chunk weighs 1 billion tons, create similar spaghetti factories. NICER telescope observed one named J0740 in the constellation Puppies, where a probe falling toward its surface would experience tidal forces strong enough to rip steel apart at atomic bonds. The numbers defy comprehension. Surface gravity 100 billion times Earth's, with magnetic fields so intense they warp the trajectories of electrons in empty space. Visualizing this requires bending physics itself. Simulations show a hypothetical titanium probe approaching a neutron star's equator. At 5,000 miles out, it's intact. 2,000, stretching begins as differential gravity tugs the near side harder. 500 miles, the probe's front half accelerates so much faster than the rear that it elongates into a shimmering strand like hot glass pulled by a master blower. By 50 miles, it's a stream of ionized particles spiraling into the star's crust at half-light speed. What makes gravity wells uniquely horrifying isn't just their destructive power, it's their invisibility. No warning flares, no shockwaves, just the silent, inexorable grip of spacetime itself twisting around you. Future interstellar travelers might navigate asteroid fields and radiation storms, but one miscalculation near a neutron star or black hole. There's no rescue, no last-minute engine burn, just the universe's most fundamental force reminding you some places aren't meant to be explored. The year was 1997, aboard Russia's Mir space station, when a routine oxygen-generating canister suddenly erupted in flames. Thick, toxic smoke billowed through the modules as astronauts struggled to contain the fire with extinguishers and towels. But the real horror wasn't just the blaze, it was how it started. A single spark, leaping between floating metal fragments in zero gravity, ignited the catastrophe. This is the nightmare of spacecraft arcing, where the very environment designed to keep astronauts alive becomes the perfect catalyst for disaster. In space, fire behaves unlike anything on Earth. Without gravity, hot air doesn't rise, it forms searing, spherical infernos that hover like malevolent ghosts. Even worse, metal shards, screws, and strands of wire don't fall to the ground. They drift, colliding unpredictably with equipment and each other. A loose bolt tumbling past a live wire might bridge a connection it never would on Earth, creating a deadly arc of electricity. NASA slow-motion footage of vacuum chamber tests reveals the terrifying mechanics. A frayed wire drifting in microgravity suddenly erupts in a blinding blue-white flare as current jumps across exposed conductors. The arc doesn't just fizzle, it sustains, feeding on the oxygen-rich atmosphere until something melts or burns. Mir's fire was a brutal wake-up call. The station's faulty oxygen generator wasn't the only culprit. Decades of accumulated debris, scraps of foil, flecks of solder, even clumps of dust had turned the station's interior into a floating minefield of conductive hazards. After the fire, Russian cosmonauts reported finding charred fragments of insulation and metal embedded in walls, evidence of secondary arcs that could have reignited the blaze. Modern spacecraft try to mitigate this with rigorous debris sweeps before launches, using sticky pads and vacuums to hunt for stray metal. The International Space Station shields critical wiring behind protective conduits, and astronauts train to seal off modules at the first whiff of smoke. But the danger never fully disappears. In 2013, ISS crew members detected a faint burning smell near an electrical panel, a warning sign of arcing they caught just in time. Had a single spark reached the station's oxygen reserves, history could have repeated itself. The bitter irony, some of the most fireproof materials on Earth become hazards in space. Aluminum, prized for its lightness, burns terrifyingly well in pure oxygen. Even stainless steel can ignite under the right conditions, as Apollo 1 tragically proved. Future lunar bases and Mars ships will need entirely new approaches, perhaps inert gas fire suppression systems, or self-healing insulation that seals breaches before arcs form. Until then, every spacecraft remains one errant screw, one frayed wire, one drifting shard away from disaster, because in the void, fire doesn't just burn. It hunts. Einstein's theory of relativity isn't just abstract physics, it's the reason your GPS doesn't lead you into a ditch every day. Those satellites orbiting 12,000 miles above Earth. Their atomic clocks tick faster than identical clocks on the ground by about 38 microseconds daily, all because time itself stretches and contracts under gravity's grip. Down here, Earth's mass warps space-time enough to slow time ever so slightly. Up there, weaker gravity lets clocks run wild. Without engineers painstakingly correcting for this drift, your phone's navigation would be off by 6 miles within a single day. But this is just the tip of the temporal iceberg. Picture a future Mars colony where the red planet's 24-hour and 37-minute sols force an impossible choice. Do settlers sync their clocks with Earth, enduring a creeping mismatch between local time and daylight, or abandon Earth time entirely, creating a temporal rift between worlds? The debate could fracture colonies. Farmers might demand a Mars-centric clock tied to sunlight, while Mission Control insists on Earth synchronization for coordination. The chaos deepens when you consider relativistic effects. Mars' weaker gravity means its clocks tick fractionally faster than Earth's, a discrepancy compounding over years. Now imagine two atomic clocks, one left on Earth, the other shipped to Mars. After a decade, the Mars clock would lead by about 200 milliseconds. That might sound trivial, but for precision systems, think interplanetary internet protocols or synchronized Mars-Earth launches. It's catastrophic. A millisecond glitch derailed the 2012 night capital trading algorithm, erasing $450 million in minutes. Now scale that to planetary logistics. The solution may be Martian leap seconds, or a hybrid system where Mars formally adopts its own time zone while key systems maintain Earth sync. But here's the twist: as humans spread across the solar system, timekeeping balkanization could follow. Europa's clocks, juggling Jupiter's immense gravity, might diverge even more dramatically. Future historians may look back at our era as the last moment when all of humanity shared the same now, before relativity shattered time into countless splinters. Because in space, even the clocks conspire against order. Hollywood got it wrong again. Those thunderous engine roars and explosive sound effects in space epics. Pure fantasy. The reality is far more unsettling. Space is a perfect vacuum, a soundless abyss where screams vanish unheard and collisions unfold in eerie quiet. This isn't just an absence of noise, it's total sensory deprivation. A void so absolute it can unravel the human mind. Apollo astronauts experienced this firsthand during their trips behind the moon, where Earth's radio chatter vanished, leaving only static silence. But something bizarre happened. Some reported hearing phantom music in their headsets, a ghostly choir of chimes and whistles with no physical source. Eugene Cernan of Apollo 10 described it as outer space-type music, while his crewmate John Young logged it officially as weird whistling. NASA later dismissed it as radio interference, but psychologists recognized the truth. The brain, starved for sensory input, will fabricate sounds rather than endure nothingness. This phenomenon isn't unique to space. Deep-sea divers and Arctic explorers report similar auditory hallucinations, the mind's desperate attempt to fill silence with something. On Earth, we're constantly bathed in ambient noise, rustling leaves, distant traffic, our own breath. Strip that away and the brain rebels. Soviet cosmonaut Valentin Lebedev wrote in his diary about hearing phantom footsteps and muffled voices during long solo shifts on Salyut 7, despite being utterly alone. The silence of space isn't passive, it's oppressive. Without sound vibrations, astronauts lose a critical spatial awareness cue, a wrench clattering to the floor on Earth. Your ears instantly locate it. On the ISS, that same wrench drifts noiselessly, potentially tumbling into critical systems before anyone notices. NASA trains crews to rely on visual tracking, but the cognitive load is exhausting, like living in a nightmare where danger moves without warning. And then there's the psychological toll. Prolonged silence amplifies isolation, turning loneliness into something visceral. Astronauts on the ISS report straining to hear anything, the hum of a fan, the creak of metal, just to ground themselves in reality. Future Mars colonists might face years of this auditory void, their only sounds coming through headphones or artificial habitat noise. Some studies suggest playing recorded Earth sounds, rainforests, ocean waves, could stave off mental decay, but it's a bandage on a deeper wound. The cruelest irony, this silence is also a killer in disguise. During emergencies, like the 2018 Soyuz leak, astronauts rely on subtle hisses or pops to detect hazards. No sound means no warning. A micrometeoroid could pierce a hull without a whisper, or a fuel line could rupture silently, its deadly fumes spreading unnoticed. So while sci-fi bombards us with laser blasts and warp-core rumbles, the truth is far more haunting. Space doesn't just starve you of air and warmth, it steals the very soundtrack of existence, leaving you alone with the deafening roar of your own thoughts. And in that silence, madness whispers. We've journeyed through the cosmos's deadliest traps, cosmic radiation shredding cells like invisible shrapnel, space debris hurtling faster than bullets, the crushing silence of isolation warping even the strongest mind. These aren't just science fiction nightmares, they're the real price of venturing beyond our blue marble. Yet here's the twist: for every danger we've uncovered, brilliant minds are crafting defenses. Look at the progress shields woven from artificial magnetic fields to deflect radiation, laser brooms sweeping orbital debris, even experiments in hibernation to outwit the psychological toll of deep space. The same vacuum that kills could become our ally, with advances in quantum communication erasing the lag between worlds and those toxic Martian soils. Microbes engineered to devour perchlorates might one day turn wastelands into farmland. This isn't blind optimism. It's the legacy of human ingenuity, the same spirit that turned fire from a threat into a tool, that transformed lightning into electricity. The cosmos throws challenges at us like a relentless puzzle master, and piece by piece we're solving them. So tell us, which hidden danger rocked you the most? The way microgravity unravels the body, the solar storms that could blind our technology. Drop your thoughts below and hit subscribe to join us for the next chapter. Because the greatest story isn't the perils we've uncovered, it's how we'll conquer them. The final frontier isn't just a place, it's a test and humanity. We're just getting started.